When people look at computers, they usually focus on what they seem to do. They notice the screen, the keyboard, the graphics, the sound, the complexity of applications. Feynman's thinking cuts straight through that surface-level fascination. He wanted people to stop being impressed by appearances and start asking a much more fundamental question. What is actually happening inside the machine? Not metaphorically, not philosophically, but mechanically. Feynman made it clear that once you understand the internal structure of a computer, its apparent versatility stops looking mysterious. A computer does not become different things. It does not transform itself from a calculator into a word processor or a game machine. At its core, it always performs the same kind of operation. The only thing that changes is a set of instructions it is following at a given moment. This idea becomes clearer when you think about memory the way Feynman did. Instructions are not alive inside the machine. They are stored. They sit idle until they are brought into action. Most of what a computer knows is locked away, inaccessible, like files in a storage room. When a particular task needs to be done, the relevant instructions are retrieved, loaded, and executed. Once that task is complete, they can be discarded and replaced with another set. What matters here is not speed alone, but organization. Feynman emphasized that execution happens very quickly, but retrieval does not. Memory is large, slow, and passive. Processing is fast, small, and active. The entire system works by constantly moving information back and forth between these two worlds. This is why computers appear powerful yet limited at the same time. They can do extraordinary things very quickly, but only when the problem has been carefully organized in advance. This leads directly into one of Feynman's most important insights. Computers are not flexible because they are intelligent, they are flexible because humans are. The intelligence is in the design of the instructions, not in the execution. Once the instructions are written, the machine follows them blindly. There is no interpretation, no judgment, no understanding. The machine does exactly what it is told, no more and no less. Feynman was very strict about this distinction. He resisted any attempt to blur the line between procedure and intelligence. If a task can be described as a definite sequence of steps, then a machine can perform it. If it cannot be described that way, then the machine has no way forward. There is no hidden intuition inside the hardware waiting to save the day. This becomes especially important when people talk about speed. Modern machines execute operations at a rate that is completely alien to human experience. Millions, billions of steps happen in the time it takes a person to think a single thought. Feynman pointed out that this speed often creates the illusion of intelligence. When a machine responds instantly, people assume it must know something. In reality, it is simply executing a prepared procedure extremely fast. As memory grows larger, another issue appears. One fast processor can only do one thing at a time. No matter how fast it becomes, it remains singular. Me. Feynman highlighted this as a practical limitation rather than a philosophical one. If one processor has to serve an enormous memory, constantly fetching and updating information, it eventually becomes a bottleneck. This naturally raises the question of parallelism. Why rely on a single processor at all? Why not use many processors working at the same time? Feynman explored this idea carefully because on the surface it seems obvious. If one clerk can process files quickly, then many clerks should be even better. The problem, Feynman explained, is not speed, but coordination. When multiple processors work on shared information, timing becomes critical. If one processor changes a piece of data while another is reading it, the outcome depends on who acts first. Without strict organization, errors are unavoidable. The processors themselves are too simple to resolve these conflicts. They cannot negotiate. They cannot reason. They simply act. For a long time, this made parallel computing seem impractical. It was easier to build faster individual processors than to design systems where many processors could work together safely. Software became the limiting factor, not hardware. Writing instructions that prevent interference turned out to be far more difficult than expected. Feynman did not see this as a dead end. He saw it as a design challenge. Instead of allowing all processors to access the same memory freely, systems could be structured so that each processor works mostly on its own data. Communication becomes rare and controlled. In such systems, parallelism stops being chaotic and starts becoming productive. He went even further and considered extremely large systems with thousands or tens of thousands of processors. These processors are not smarter than a single one. In fact, they are usually simpler. They all receive the same instruction and apply it to different pieces of data simultaneously. The power comes from numbers, not sophistication. This idea reflects something very deep in Feynman's thinking. Progress does not always come from making things more complex. Sometimes it comes from stripping systems down to their simplest elements and scaling them up. Whether this works depends entirely on how well the problem itself has been structured. From here, Feynman shifted attention away from machines and toward capability. What can computers actually do? His answer was precise and deliberately limited. Computers can do anything that can be expressed as a clear procedure. They can follow rules. They can execute algorithms. They cannot operate outside those boundaries. This distinction becomes critical when people talk about intelligence. Machines that play chess or recognize patterns appear intelligent because the tasks have been reduced to formal procedures. The machine does not understand chess. It does not see strategy. It evaluates positions, explores possibilities, and applies predefined rules at extreme speed. Humans, by contrast, operate very differently. People do not examine millions of possibilities. They recognize patterns, ignore irrelevant options, and act on intuition. Feynman openly admitted that we do not fully understand how this process works. Because we cannot describe it precisely, we cannot mechanize it. This is not a weakness, computers. It is a clarification of what they are. Machines excel at what can be formalized. Humans excel at what cannot yet be reduced to rules. Confusing these strengths leads to false expectations and unnecessary fear. Feynman's message here is not about competition between humans and machines. It is about clarity. Computers are powerful because they are simple, fast, and reliable. Their future depends not on making them resemble human minds, but on learning how to describe problems in ways that machines can execute. This understanding sets the stage for deeper questions about learning, heuristics, and where procedure ends and creativity begins. Once this boundary between procedure and intuition is clear, Feynman's thinking moves into a more subtle and often misunderstood territory. Learning. Many people hear the phrase, learning machine, and immediately imagine a system that improves itself in a human-like way, almost as if it gains experience or insight. Feynman was very careful here. He did not reject the idea of machines learning, but he insisted on precision. Learning, in a computational sense, does not mean understanding. It means modifying behavior according to rules that were already defined in advance. At its core, a learning machine is still following instructions. The difference is that some of those instructions allow parameters to change. The machine does not decide how to learn. It is told how learning should occur. Feynman emphasized that this distinction matters because it prevents us from attributing mystery where none exists. The machine is not discovering new principles. It is adjusting values within a framework designed by humans. This idea becomes clearer when you think about trial and error. Feynman pointed out that trial and error is often mistaken for intelligence, but it is actually one of the simplest procedures imaginable. Try something. If it works, keep it. If it fails, discard it. Repeat. A machine can do this extraordinarily well, not because it understands success or failure, but because success and failure have been defined numerically. A score improves or it does not. The machine follows the numbers. Feynman saw no magic in this process. In fact, he considered it almost trivial from a conceptual standpoint. What matters is not that machines can perform trial and error, but that humans choose meaningful criteria for success. If the criteria are poorly chosen, the machine will optimize the wrong thing perfectly. Speed and precision will only amplify the mistake. This leads to Feynman's deeper concern, the danger of confusing optimization with intelligence. Machines are excellent at optimizing measurable quantities. They can maximize efficiency, minimize error, or reach targets faster than any human could. But optimization does not tell us whether the target itself makes sense. That judgment remains entirely human. Feynman often returned to this theme because he believed it exposed a broader misunderstanding about technology. People tend to focus on what machines can do and forget to ask why they are doing it. A machine that performs flawlessly can still be solving the wrong problem. No amount of speed or learning will correct a poorly framed question. From here, Feynman shifted toward heuristics. Unlike strict procedures, heuristics are rules of thumb. They are not guaranteed to work, but they work often enough to be useful. Humans rely on heuristics constantly. We simplify problems, make assumptions, and accept approximate answers. Feynman found this fascinating because it sits right at the edge of what machines can and cannot do. He argued that heuristics can be programmed, but only in a limited way. A machine can be told to prefer certain paths over others or to stop searching once a solution is good enough. But the machine does not know why a heuristic is reasonable. It applies it blindly, just like any other instruction. The effectiveness of the heuristic depends entirely on how well it matches the structure of the problem, This explains why machines can sometimes outperform humans dramatically in narrow domains while failing completely outside them. When the structure of a problem is well understood and stable, heuristics can be designed that work exceptionally well. When the structure changes or becomes ambiguous, those same heuristics can lead to catastrophic errors. Feynman believed this revealed something important about intelligence itself. Human intelligence is not just a collection of rules. It is deeply tied to context. Humans constantly adjust which heuristics they use based on subtle cues, many of which they cannot articulate. This flexibility is not yet something we know how to formalize. Rather than seeing this as a challenge to be solved immediately, Feynman treated it as a boundary to be respected. He warned against overconfidence. Just because a machine performs impressively in one domain does not mean it possesses general intelligence. It means the domain has been carefully constrained. This naturally leads into the topic of simulation. One of the most powerful uses of computers, in Feynman's view, is their ability to simulate systems that are too complex to study directly. Instead of solving equations analytically, machines can model behavior step by step and observe the outcome. This approach has transformed science not by replacing theory, but by extending it. Feynman stressed that simulation is not explanation. A simulation can reproduce behavior without revealing underlying principles. You may know what happens, but not why it happens. This distinction mattered deeply to him as a physicist. Understanding, for Feynman, always meant uncovering the simplest underlying mechanism. He was cautious about treating simulations as truth. A simulation is only as good as the assumptions built into it. If those assumptions are wrong or incomplete, the results may be misleading, even if they appear convincing. Once again, the machine executes flawlessly, and once again, the responsibility lies with the human designer. This pattern repeats throughout Feynman's thinking. Computers magnify human intentions. They do not replace them. They are extraordinarily good at carrying out clearly defined tasks at scale. They are powerless when definitions are vague or goals are confused. As the discussion continues, Feynman returns to the idea of limits. There are problems that machines cannot solve, not because they lack power, but because the problems themselves are undefined in procedural terms. Questions that rely on meaning, interpretation, or value judgments fall into this category. A machine cannot decide what matters unless it is told. This does not mean such problems are unimportant. On the contrary, they are often the most important ones. But Feynman insisted on honesty, pretending that machines can answer questions they are not equipped to address only creates confusion. At the same time, Feynman rejected pessimism. He did not believe that the limits of machines imply limits on progress. Instead, he believed that understanding those limits allows us to use machines more effectively. When we stop asking computers to be human, we can start asking them to be excellent tools. This brings the discussion back to a central theme: clarity. The power of computers comes from their simplicity. They execute procedures reliably and at immense speed. Everything else, the intelligence, the purpose, the meaning, comes from the way humans frame problems and interpret results. By the end of this section, Feynman's position is unmistakable. Computers are not mysterious thinkers hiding behind screens. They are precise instruments. Their greatest danger is not that they will surpass human intelligence, but that humans will misunderstand what they are actually doing. This understanding prepares us for the final stage of the discussion, where Feynman confronts the future directly and asks what role machines should play in human life. When Feynman turns toward the future, his tone becomes both cautious and grounded. He avoids predictions framed as hype or fear and instead returns to first principles. The future of computing, in his view, is not about machines becoming something entirely new. It is about humans becoming clearer about what machines already are and how they should be used. One of the strongest ideas in this part of Feynman's thinking is responsibility. As computers become faster, cheaper, and more widely available, the temptation is to hand over more decisions to them. Feynman warned against doing this blindly. A machine can execute decisions at scale, but it cannot evaluate the consequences of those decisions unless those consequences have been explicitly defined. Delegation without understanding is not progress. It is abdication. Feynman was especially concerned about authority. When a computer produces an answer, people tend to treat it as objective or final. Numbers feel neutral. Calculations feel trustworthy. But Feynman insisted that every output reflects assumptions, simplifications, and choices made earlier. If those choices are flawed, the result will be flawed as well, no matter how impressive the computation looks. This is why Feynman emphasized transparency. Systems should be designed so that humans can understand what they are doing, at least in principle. A tool that cannot be explained is a dangerous tool, not because it is malicious, but because it encourages uncritical acceptance. Feynman believed that understanding must scale along with power. He also addressed the idea of automation replacing human judgment. Certain tasks, especially repetitive or well-defined ones, are ideal for machines. Removing humans from these processes can reduce error and increase efficiency. But Feynman drew a clear line. When a task involves values, priorities, or trade-offs that cannot be reduced to numbers, human judgment remains essential. This distinction matters because it shapes how technology affects society. Feynman did not see computers as neutral forces. They amplify whatever structure they are placed into. In a well-designed system, they increase productivity and insight. In a poorly designed one, they accelerate mistakes. Feynman also challenged the belief that complexity itself is a sign of progress. As systems grow larger, they often become harder to understand, not easier. Layers of abstraction hide underlying mechanisms. When something goes wrong, no one knows where to look. Feynman found this deeply troubling. For him, understanding was not optional. It was the core of scientific responsibility. He argued that elegance and simplicity are not aesthetic preferences. They are practical necessities. A system that cannot be reasoned about cannot be trusted. This principle applies just as much to software and algorithms as it does to physical machines. As computing power increases, Feynman believed the real challenge would shift from hardware to ethics and design. Not moral philosophy in the abstract, but concrete questions. What should be automated? What should remain under human control? Who is accountable when automated systems fail? These questions cannot be answered by machines, no matter how advanced they become. Feynman rejected the idea that progress is inevitable or self-correcting. Technology does not automatically lead to better outcomes. It magnifies both wisdom and foolishness. The difference lies in how carefully it is used. He also addressed the fear that machines might one day dominate human decision-making. Feynman considered this fear misplaced. Machines do not want anything. They do not pursue goals. They carry out instructions. The danger is not that machines will take control, but that humans will stop paying attention. This brings his thinking full circle. From the simplest internal operations of a computer to its most complex applications, the same principle applies. The machine does exactly what it is told. If the result is surprising, confusing, or harmful, the cause lies upstream, in the assumptions, the instructions, and the goals defined by humans. Feynman believed that education plays a central role here. People should not merely use computers. They should understand them. Not at the level of electrical engineering necessarily, but at the level of logic and structure. Without this understanding, Society risks becoming dependent on tools it does not comprehend. He was optimistic, but not naive. Feynman trusted human curiosity and intelligence, but he also knew how easily people could be distracted by surface-level impressions. The flashing lights, the speed, the complexity, all of these can obscure the simple truth of what a computer actually is. In his view, the most productive future is one in which machines are treated as extensions of human reasoning. Not replacements for it. They should handle the mechanical burden, allowing humans to focus on creativity, interpretation, and meaning. This division of labor respects the strengths of both. Feynman's final message is not about computers at all. It is about thinking clearly. Tools do not absolve us of responsibility. They sharpen it. The more powerful our machines become, the more careful we must be in deciding how to use them. If we understand computers for what they truly are, fast, obedient, and fundamentally simple, we can use them wisely. If we project intelligence, intention, or authority onto them, we risk misunderstanding both the machine and ourselves. That clarity, for Feynman, was the real future worth building.